All right, so let's go over the problem right now. It wants us to find the fifth term in this recursive sequence that starts with 3, and an equals 2 times the previous term plus 3. So we can just list out the first few terms using that table. So let's have an be here and n be on this side. A1 is 3, and then for n equals 2, we double it and add 3. So that would give us 9. And then for the third term, we double 9 and add 3, which is 21. And then same for the fourth term. And then we get that the fifth term is 93. Any questions about this? All right, let's move on. So later on, we'll discuss how to find a closed form expression. So that's basically a formula that doesn't involve the other terms of the sequence. And we'll do that for basically a specific kind of recurrence relation. But for other types, we are sometimes able to find a closed form if the conditions are right. So for example, let's look at the one here where the 0th term is 1 and an equals n times an minus 1 for all positive integers. So if we look, an equals n times an minus 1. And then that means an minus 1 is n minus 1, an minus 2, and so on. So if we keep going, we'll find that it's n times n minus 1 times n minus 2, all the way down to a0, which is 1. And you might notice that this is equal to the factorial formula. So in this case, an would equal n factorial. All right, so let's look at this checkpoint, and feel free to type your answer into the chat when you think you figured it out. All right, it's been about a minute. Would you guys like to keep working, or do you want to go over the answer right now? Okay, so let's just talk about it now. So we're trying to find a closed form expression for the sequence defined by an equals n times n minus 1 times a n minus 1. And the first term is 2. So let's try the same thing that we did last time. So we have n times n minus 1. And then for the previous term, we can substitute in n minus 1 times n minus 2, and then a n minus 2. And then this is also equal to n minus 1, n minus 1, n minus 2, another n minus 2, n minus 3, and then a n minus 3. So if we keep going, it looks like what we'll get is something like n times n minus 1 squared, n minus 2 squared, and so on all the way down to 2 squared. And that is also the same as n times n minus 1 factorial squared. So this would be a closed form expression for this sequence. All right, now let's look at a closed form closed form formula for a different kind of recursive relation. So in this one, the first term is 4, and what we're doing is we're subtracting 5 from the previous term. So if we list out a few of the values, the first one is 4, and then minus 5 means that the next one is negative 1, and then negative 6, negative 11, and so on. This is 6, sorry. Okay, so that means that if you take a close look, it looks like it's just an arithmetic sequence where every time we're subtracting 5. So the common difference would be 5, negative 5. So since the first term is 4, we can write it as an equals 4 minus 5 times n minus 1. So that's another way we can rewrite a recursive sequence as a closed form. So let's take a look at this example now. And again, type your answer into the chat when you think you've got it. Oh yeah, and I also forgot to mention that we'll have the same schedule as always. We'll take a short break at 2:55, and then after that we'll have a Kahoot. All right, so for this one, let's start a few values again. So the first term is 7, then we multiply it by 5, and then we multiply that term by 5 again. So since we're multiplying by 5 each time, this is an exponential function with a common ratio of 5. So that means we can write it as a(n) equals 7 times 5 to the n minus 1. This slide is out of order, sorry. Okay, so sometimes we'll now shift to looking at some more competition-based problems where you might have something called a periodic recurrence, and that means that the values produced by the recursive formula will repeat regularly. So if this is the case, then you usually don't have to find a closed form for the equation. You can just look for a pattern and then use it to get the answer. So we'll take a look at this example from one of the Amy problems this year. So first off, we have this recursive relation with the first term is 20, the second term is 21, and then the nth term is 5 times tn minus 1 plus 1, and then over 25 times tn minus 2. So to make things a little bit easier, let's let t1 equals a and t2 equals b. So it wants us to find t2020, the 2020th term. So this value probably isn't very big, otherwise it would be very difficult to compute. So it's pretty likely that we're dealing with a periodic recurrence here. So with that in mind, we can try to plug in a few values and find a pattern. So if you go to T3, the previous term would be b, so that the top is b 5b plus 1, and then over 25a. All right, so now let's look at what the fourth term is. So we plug the previous term into the numerator, and that will give us 5b plus a, 5b plus 1 over 5a since we multiplied by 5, and then plus 1 over 25b. And if we simplify that, that's 5a plus 5b plus 1 over 125ab. Let's see. Okay. Okay, now let's look at the fifth term. So again, we plug in the previous term into the numerator. And unfortunately, it does get a little bit messy here. Then again, we add 1, and then the stuff on the denominator would be 5b plus 1 over a. And this turns out to be 5a plus 1 over 25b. Okay, and then let's skip some of the algebra here, but t6 equals a, and then t7 equals b. So now we're back to a and b. And then since this relation only relies on the last two terms. Once we've gotten A and B, that means that the pattern will repeat for the rest of the numbers. So it looks like it starts to repeat after T5. After 5 terms, it repeats. So that means that 2020 is divisible by 5, so it will have the same value as the 5th term. And that means we just have to compute 5 times A plus 1, just 5 times 20 plus 1 over 25 times 21. And that will give you 101 over 525. So any questions about this one? All right, we'll move on to this checkpoint and let us know once you've gotten an answer. Okay, it's been about a minute. Do you guys want some more time to work on it, or do you want to go over the answer right now? All right, let's talk about it now. So, this is going to be periodic again. And since AN is the remainder when F is divided by 3, there are only 3 possible values, 0, 1, or 2. So let's make a table again. So oops, we should have started from 1. Not 1, 0. All right, so 0 is 0, 1 is 1. And then 0 plus 1 is 1, which is still 1. 1 plus 1 is 2. Now 1 plus 2 is 3. And when we divide that by 3, the remainder is 0, so now it's 0. So we can just add the remainders together, and that would give us the next one with a remainder of 2, and then 2 again, and then 2 plus 2 is 4. When divided by 3, that gives a remainder of 1, and then 1 plus 2 is 3 again, so remainder is 0. And 1 plus 0 is 1. So we are back to the beginning again, because the Fibonacci sequence only depends on the previous 2 terms. And we've just gotten the same 2 terms again. So that means that this sequence is going to repeat every 8. And to make things a little bit easier, we'll start counting from here. So every 8 it will repeat. Now 2020 is not divisible by 8, but it is divisible by 4. So that means it's 8 times some number plus 4. So when we divide 2020 by 8, we'll get a remainder of 4. And that means it will share the same value as the 4th term in this group, which happens to be 0. So a 2020 equals 0. All right, let's move on now. And now we'll talk about the linear homogeneous recursion closed forms that we mentioned briefly at the start. So this is a kind of a mouthful to read, but a linear homogeneous recurrence relation is a recurrence relation defined by an equals c1 an minus 1 plus c2 an minus 2, and all the way up to cm times an minus m. And there are a few things we have to keep in mind. All the n have to be greater than k. All the c's are real constants, and m and k are non-negative integers where k is greater than m, and the c's cannot be, cm is not equal to 0. So what do all of these terms mean? Linear means that the sequence has all the a's raised to the power of 1. So notice how all of these are not powers of 2, not powers of 3, but they're powers of 1. So that makes it linear. This relation is homogeneous because every term on the right-hand side has the same degree. And like we saw, the same degree is 1. But if they do not have the same degree, then it would not be homogeneous. And finally, constant coefficients means that the coefficients are all constant numbers. So let's check your understanding of what makes something linear, homogeneous, and constant coefficients. So for the first one, is this one linear, homogeneous, and constant? If not, which ones do they mean? And if you want to type your answers in the chat, you can use L for linear, H for homogeneous, and C for constant coefficients. Okay, well, this one is linear since A is raised to the power of 1, and homogeneous since there's only one term, so it has the same degree. But it does not have constant coefficients because we have an n here, and that obviously changes with whatever n is, and that means it's not constant. So the first one is linear and homogeneous only. Now for the second one, it is not linear because the degree of this term happens to be 2, since we have two terms multiplied together. So it's not linear. But once again, since there's only one term here, it's homogeneous, and the coefficient is 1, so that means it has constant coefficients. All right, for number 3, we have a constant c times a n minus 1. So this one meets all 3 criteria. It's linear. A n minus 1 is to the power of 1. It's homogeneous because there's only one term, so they all have the same degree. And we're given that the constant c is constant, so it has constant coefficients. All right, now for the next one, once again it's linear because all of the a's are raised to the power of 1. However, it is not homogeneous because we have this 3 here, and this 3 does not have a corresponding a with it. So that means that the a is raised to a power of 0, which is different from these, which are raised to a power of 1. So they are not all the same degrees, so it's not homogeneous. But the coefficients are all constant. We have 2, 1, and 3. Okay, now moving on to number 5. Right off the bat, we can see that it's not linear because these are squared. However, it is coefficients because they are both squared. And they are both homogeneous, I mean. And we also have constant coefficients since both coefficients are equal to 1. Okay, and then this one, you have to be careful because we actually have a n plus 1 here. However, this is still fine because we can rewrite it so that a n plus 1 is on one side, and we have 0.5 an plus 1.5 an minus 1. So it turns out that this is also linear since all of the a's are the same degree, and that's 1, homogeneous, and the coefficients are all constant. For number 7, we see that it's squared, so this is not linear. It's also not homogeneous because one of these is 2, the other one is 1. But the coefficients are constant, so it only satisfies one of the conditions. And finally, for number 8, we see that it's linear since all the terms have degree 1, and that also makes it homogeneous. And then the coefficients are 2 and -3, which makes it have constant coefficients. Okay, now we'll keep going. So the characteristic polynomial of a linear homogeneous recurrence, so this is the same thing we were talking about earlier. This thing has something called a characteristic polynomial. And what that is this polynomial that's formed out of all of these coefficients here. So notice how C1 goes there, C2 goes there, and then Cm goes at the end. And also notice that the x is raised to the degree of whatever m is. So if you had something like an equals an minus 1 plus an minus 2, that means m is 2. So we would raise this power to 2. And then the last coefficient does not have any x attached to it. After all the x's, the degrees are decreasing across the entire polynomial. So what can we do with this characteristic polynomial? Well, now we have this theorem that says that if we have this characteristic polynomial, then if p of x has roots that are distinct, then the sequence an would also equal to b1 times one of the roots to the kth power plus b2 times one of the roots to the another one of the roots to the kth power, and then so on for all of the roots. And this is really powerful because now we can get a closed form of a recurrence relation with this formula right here. Now you may be wondering, how do we get the b since they don't show up anywhere here? Well, we'll talk more about that once with this example of the Fibonacci sequence. So if you recall, the Fibonacci sequence was defined this way. Fn equals Fn minus 1 plus Fn minus 2. And the 0th term was 0, and the first term was 1. So we can see that the characteristic polynomial in this case would have to be x squared because of the 2 here. And then both coefficients are 1, so we have minus x minus 1. And then you can find the roots of this using the quadratic formula or completing the square, but it should give you something like 1 plus root 5 over 2 and 1 minus root 5 over 2. So that means that Fn equals b1 times 1 plus root 5 over 2 to the n plus b2 times 1 minus root 5 over 2 to the n. So now what's left is we just have to find out what b1 and b2 are. To do that, remember that we know that the 0th term is 0 and the first term is 1. So that means we can plug in n equals 0 and n equals 1 to get a system of equations. So if we plug in 0, both of these go to 1. So that means b1 plus b2 equals 0. And then also, if we plug in 1, we get b1 times 1 plus root 5 over 2 plus b2 1 minus root 5 over 2 equals 1. So this is our system of equations. Now, if we solve this, I'll skip some of the algebra to save some time. But b1 equals 1 over root 5, and b2 equals negative 1 over root 5. And that means that Fn equals 1 over root 5 times this thing minus 1 over root 5 times this other thing. All right, so now we have a closed form for the Fibonacci sequence. And if you're curious, you can plug in a few values for n on your own, but this will give you the nth term of the Fibonacci sequence. Now, you can try it on your own with this checkpoint, which is called the Pell sequence. So let's talk about it in a few minutes. All right, let's start talking about this now. So, first we can get what the characteristic polynomial is. The first coefficient is 2, and the second one is 1. So that means it's x squared minus 2x minus 1. Okay, and then if we solve this, we basically find that the roots are 1 plus root 2 and 1 minus root 2. So P of n equals some constant b1 times 1 plus root 2 to the n plus b2 times 1 minus root 2 to the n. Now we can do the same thing that we did last time and set up another systems of equations with 0 and 1 here. So once again, we have b1 plus b2 equals 0. And the other one would be b1, 1 plus root 2 plus b2 minus root 2 equals 1. Okay, and now if we solve this, we get that b1 equals 1 over 2 root 2, b2 equals negative 1 over 2 root 2, and for a final answer, sorry, I'll put it here just because I'm running out of space, Pn equals 1 over 2 root 2 times 1 plus root 2n minus 1 over 2 root 2, 1 minus root 2n. Yikes. Okay. So that's how we can use the characteristic polynomial to get the closed form. Now we can take a look at a problem where we might use this. So we have the sequence an that's defined recursively. The 0th term is 1. The first term is the 19th root of 2, and an equals an minus 1 times a squared n minus 2. So what's the smallest possible positive integer k such that this product, a1 times a2 all the way to ak, is an integer? So first we have to find a good way to express the recursion, since we don't want to deal with it here. Unfortunately, this is not linear and it's not homogeneous because of the squared here, and they're multiplied together. A trick we can use to make it linear and homogeneous is to take some logarithms. Notice, if you remember from last week, if we take the logs of two things that are multiplied together, that's equivalent to adding them. So in that case, we can take log 2 an equals log 2 an minus 1 plus 2 log an minus 2. And we chose base 2 because the first term is the 19th root of 2. And if we go with 2, that would make some computation easier in the future. So now what we can do is let bn, so we're defining a new sequence here, equal 19 log base 2 of an. And then that means now we can write bn as this sum here. So bn minus 1 plus 2bn minus 2. And we'll do the same thing with the characteristic polynomial. In this case, it's x squared minus x minus 2, which we can factor. And that means that Bn is C1 negative 1 to the n plus C2 2 to the n. And once again, we set up the system of equations. Oh yeah, I forgot to mention that if we do it like this, we can let B0 equals 0, and then B1 equals 1. And that can make, that lets the rest of the recurrence be correct. So if we it started with these two values, then C1 plus C2 equals 0, and what's the other one? Negative C1 plus 2C2 equals 1. And if we solve that, we get C1 equals negative 3, C2 equals 1/3. And sorry, we're running out of space again. But basically, Bn equals negative 1/3, negative 1 to the n, plus 1/3 to the n. And we'll rewrite this as 2 to the n minus negative 1 to the n over 3, just by putting things over a common denominator. So now let's go back to A. Remember that we said that Bn equals 19 log 2 an. So if we make this an exponent instead, that means that an equals 2 to the Bn over 19. And remember that we're looking at this product here. So A1 times A2 all the way to AK equals 2 B1 2 B2 over 19 all the way to 2 BK over 19. And if you, from the exponent rules, we can all put this all over 2, and it will be a sum. B1 plus 19, B2 over 19, and all the way to BK over 19. So now let's think about what it means to add up B1, B2, and so on, all the way to BK. So we can split this into a few cases. So if K is even, remember that we have this formula here. This sum equals 2 to the 1 minus negative 1 plus 2 squared minus just 1 plus 2 cubed plus 1 dot 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 all the way to 2 to the n minus 1. And since K is even, all the ones will cancel, and that leaves us with 2 plus 2 squared plus 2n over 3. And sorry, there are dots here. And if you remember that 1 plus 2 plus 2 squared plus dot 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 all the way to 2 to the n equals 2 to the n plus 1 minus 1. Then we see here that we're just missing the 1, so we just subtract another 1 from this. So that's 2 to the n plus 1 minus 2 equals over 3. So that's what the sum is if K happens to be even. If K is odd, however, it's a slightly different process. So if k is odd, then the same sum would have, once again, 2 minus -1 plus 2 squared minus 1 plus 2 cubed plus 1. But this time it would end on a 2 to the k plus 1. So we would actually have 1 plus 2 squared all the way to 2 to the k over 3. And remember that it was equal to 2 to the k plus 1 minus 1 over 3. So that's what the sum is if k is odd. Okay, and now we have to use some number theory. So from this sum, clearly this product is only an integer if b1, b2, if this sum is divisible by 19. So that means that these two expressions we got have to be divisible by 19. In other words, 2 to the k plus 1 minus 2 is divisible by 19, and 2 to the k plus 1 minus 1 is divisible by 19. So using something called Fermat's little theorem, we get that 2 to the 18 is equivalent to 1 mod 19. And this is useful because you can modify it a little bit to get 2 to the 18 minus 1 is congruent to 0 mod 19. And also, if we multiply both sides by 2, 2 to the 18 times 2 is congruent to 2 mod 19. And that's the same as 2 to the 19 minus 2 is congruent to 0 mod 19. So notice that these are all in the forms here. So for this one, k equals 17. And for this one, k equals 18. So these are our two solutions, 17 and 18. And since 17 is the smallest possible positive integer k, this would be our answer. All right, I know that this is pretty long, but we'll just quickly go over some applications of recursive functions in combinatorics. So let's take a look at this one real quick. And it says, find the number of 10-digit positive binary numbers that do not have a pair of consecutive zeros. So let's think about it. Let's start with a 1-digit positive binary number. The only possibility is 1. And then for 2-digit positive binary numbers, the only possibilities are 1, 0 and 1, 1. So let's try to think about it recursively. If we start with 1, we can get a number that does not have a consecutive 0 by adding a 0 onto the end. Or we can also add in a 1 onto the end as well. So there are two possibilities. We can either add on a 1 or add on a 0 to get a 2-digit positive number, positive binary number with no consecutive zeros. Now for a number that ends in 0, it's slightly different because we can add on a 1, but we can't add on a 0 because then we would get a pair of consecutive zeros. So how can we think about this recursively? Well, let's say an is the number of n-digit numbers that end in, let's see, end in 0. Okay, and then bn is the number of n-digit numbers that end in 1. I apologize for my sloppy handwriting. But for an, we can only add on a 1 to the end of a 0-digit number. So that means an is equal to bn minus 1. But for bn, we have more possibilities. We can add on a 1 to the end of a number that ends in 1. So that's an minus 1. And we can also add on a 1 onto a number that ends in 0. So that's bn minus 1. So the total is, now that we have this recursion, we can make a table for it here. So it goes through all the n from 1 to 10. And at every step, we can compute the new an, which remember is the previous b term, and a new bn, which is the previous a term plus the previous b term. And if we do that, then we get a10 equals 34 and b10 equals 55. And that means that the total number is equal to the sum of these, 89. So there are 89 10-digit positive numbers that do not contain consecutive zeros. We'll skip this example since we're running low on time. But let's actually take a look at this checkpoint real quick before taking our break. So yeah, we'll talk about it in about a minute, and type your answer into the chat once you got in a good idea. Right, the trick is to use recursion. Solve this using recursion. I'm replying to Richard, who said that there's supposedly a trick. Okay, so I'll just start talking about it just because we're running a little bit tight on time. So let's think of a way to solve this recursively. An. So first, let's let an be the number of ways you can climb up n steps. Okay, so let's see. You can either take a 1 step or 2 steps in a jump. So let's say he's at step n minus 1. He takes a 1 step jump, and that means he's now at step n. Alternatively, he can start at the n minus 2 step, take a 2 step jump, and now he's at n as well. So if you notice, if there are there are an minus 1 ways to get to the n minus 1th step. And we can just add a 1 step. So that is a way to get to the nth step as well. And then same for the number of ways to get to the n minus 2th step. Once we get there, we take a 2-step jump and get to the nth step. So that means that the n minus 2 step is the number of ways to get to the n minus 2 steps. It's also part of the number of ways to get to the nth step. So if we sum these together, it's the total number of ways to get to the nth step. And now, if you notice, this is very similar to the Fibonacci sequence. A1 would be 1, A2 would be 2, actually. And now we just have to find what A10 is. So we just keep adding stuff together. 1, 2, 3, 4, 5. And there should be 89 ways to get to the 10th step. All right. Now we'll take a break and we'll start the Kahoot when we get back. So through our 9, we'll start the Kahoot. And feel free to ask any questions about the recursion or the lesson today during the break if you want. Give them like 30 seconds. Okay, 10, 9, 8, 7, 6, 5, 4, 3. Where's this one? Yeah, let's talk about this one. So all right, we know what A1 is. So using that, we can get what A2 is. So A2 or A1 plus 1 is A1 plus A1. So 1 plus 1 plus 1 times 1, which equals 3. Okay, so now let's find A3. And that's 1 plus 2. So A1 is 1. A2 is 3. And then 1 times 3 is 3. So this is... Oh, no, wait, sorry. This is 1 times 2, sorry. So this is 6. Okay, and then let's find A6 now. Or A3 plus 3. So A3 was 6 plus 6. And then times 3, plus 3 times 3, which is 9. So this is 21. And to get A12, we have to do A6 plus 6. So 21 plus 21 plus 6 times 6, which is 36, and that is 78. So the answer was 78. Congratulations to Shrug in first place. 10-way tie for first place. All right, nice. All right, so we're just rolling the pentagon around. So we add all these numbers up and see what the remainder is when we divide 2009 by it. And it turns out that it lands on the CD side. So nothing too complicated about this one. Congratulations, Kazuichi Soda. Oh my god. I'll take the answer. Right, not bad. So this one should be familiar because we did a similar example. But it wants us to find the sum of 8 numbers. And since this repeats, we can just add up all 8 numbers to get the answer, which happens to be 9. All right. Possibly loser is in first place now. All right. I guess the easiest way to do this might be to list out the first three terms and then find a pattern. And in that case, it turns out to be you multiply the n by 6, and then 6 is on the numerator. That's interesting. Well, turns out that this one is periodic. I believe that it repeats. Let's see. I believe it goes 2, 3, 3 over 2, 1/2, 1/3, 2/3, and then it's back to 2, 3. So once you know that it repeats, you can find out what a 2006 is. Right. The problem is to calculate the self-time. right, nice. So you want to do this in terms of the exponents, since the numbers can get pretty big. But notice that you're just adding on the exponents, and it turns out that it's the Fibonacci sequence. All right, so this one you got to do a little bit of thinking, because each AI is equal to the sum of all the previous terms. Then if A19 equals 99, that means all the previous terms, so A1 plus A2 all the way to A18, their sum is 99. And we want to find A20. So in order to do that, we just add the sum of the first 18 terms to the 19th term, which happens to be 99 plus 99, which is 198. Interesting. So I don't know, a fast way to do this is to just notice a pattern again, because 100th term is even, and if we look at all the even terms, 2, 5, 11, 23, if we add 1 to those, it's just 3, 6, 12, 20, 24. So the powers of 2 will be 0, 1, 2, 3, and so on. So with 2 is the first even number, and it's 0. So 100th is the 50th even number, and k will have to be 49. All right, so the neat thing about this is that we don't actually need to care that the first term is 97. It doesn't matter because x2 times x1 is just 2. x4 and x3 is just 4. x6 and x5 is just 6. And so on for 8. So the answer is just 2 times 4 times 6 times 8, 384. All right, last question. Okay, yeah, so if you multiply the cube roots of 3 times together, and raise the cube root of 3 to the third power, you get 3, so it's now an integer. And it's 4. That would mean that n is 4 if you do that. That's the way it is. 38% correct. We'll work on that. Yeah, thank you guys for coming. Hopefully you had fun. The handout will be available on our website soon, and also the recording. Please submit your exercise answers to our leaderboard, and sign up for the math tournament if you haven't already. Otherwise, thank you for coming, and you're welcome to leave now.